everyone. My name is Fedor Kozlov. I'm a software engineer at Facebook. Together with my colleague Isabella Yuen, data scientist at Facebook, we're going to talk about our method of evaluating changes to fake account verification systems. Online social networks, OCNs, such as Facebook, Twitter, or LinkedIn, provide a broad set of features enabling more than 2 billion people to share news, media, opinions, and thoughts. The scale and scope of these OCNs in turn attract highly motivated attackers who seek to abuse this platform and their users for political and monetary gain. The prevalence, impact, and media coverage of harmful social media accounts has increased with the growth of the platforms. A key contributor to this problem is fake accounts that do not represent an authentic user and created for express purpose of abusing the platform or its users. According to Community Standards Enforcement Report, Facebook estimates as much as 5% of their monthly active users to be fake. Recent research about online human-bot interactions, detection estimation and characterization estimates as much as 15% of all Twitter accounts to fall in this category. Fake accounts can be divided into 3 broad classes. Automated fake accounts, sometimes called social bots, are software-controlled profiles that can post and interact with legitimate users via a social network communication mechanism, just like real users. Usually, social bots are created at scale via automated registration of new accounts. The types of abuse caused by social bots vary and include misinformation, data scraping, and fake engagement. In contrast, manual-driven fake accounts are set up for a specific purpose without using automation, and are then operated manually by attackers to gain personal benefit or push propaganda. The close similarity between actual users and manually driven fake accounts breaks traditional at-scale detection techniques, which focus on identifying automated behaviors. Hybrid fake accounts, sometimes called cyborgs, include fake accounts driven by bot-assisted humans or human-assisted bots. Cyborgs are often used for the same purpose as social bots, such as spam and false news. In order to classify fake accounts, Facebook uses a team of specialists to review accounts. Reviewers look at specific signals that can indicate whether an account is real or fake. We leave a specified time to classification to allow the signals to occur. For this work, we treat such labeling as ground truth. The definition of what constitutes abusive and benign behavior is specific to OCN. For example, at Facebook, these labels are defined by community standards document. The topic of detection of fake accounts is actively explored in recent literature. Detection frameworks can be based on different methodologies. In order to detect fake accounts in OCNs, frameworks explore connections between identities, their properties in the social graph, their behavior, and interaction between different OCNs. The variety of behaviors exhibited by fake accounts, especially those controlled by humans, makes building accurate detection systems a challenge. On a platform with billions of active users, a detection system with even 99% precision would incorrectly identify hundreds of thousands of users every day as malicious. It follows that OCNs require remediation techniques that can tolerate false positives without incurring harm while still providing significant friction for attackers. A common OCN remediation technique is to enroll fake accounts detected by a detection system into a verification system aimed at blocking access to the OCN for fake accounts and providing a way to recover an account for legitimate users. Verification systems are composed of challenges which prompt identified users to prove some additional information, such as phone numbers, recent activity, or identity verification. These challenges take the form of challenge response tests that are designed to be easy for real users to pass, but difficult for attackers to solve. The best known example of such challenge is Google reCAPTCHA. The challenges provide an opportunity to collect additional signals about the user, for example, time to solve, which can aid in further investigation, reclassification, and remediation. Despite these advantages, Attackers can adapt to overcome the friction posed by verification system challenges. In addition, increasing the friction of the challenge might affect real users and make it harder for them to recover their accounts. It follows that continuously iterating on the design of those challenges and being able to measure effectiveness of iterations over time is an important component of improving fake account defenses. We seek to understand iteration effectiveness, which is the degree to which a new or improved challenge is more successful in both stopping fake accounts and letting real users through. To compare effectiveness, we subject pools of accounts to two different experiences in an A/B test experiment and compute the change in the proportion of fake and real accounts that manage to successfully pass the verification process. This computation is particularly challenging as it involves determining the true nature of the set of users that were already identified as fakes with high probability by Intrusion Detection framework. One could leverage human labeling of accounts at various stages within and after the verification process. However, relying on human labeling limits the scale and speed of the experiment. This is especially true when we require that many experiments can run at the same time, and experiments must be powerful enough to show results on different user segments, for example, different platforms or different locales. So we need to find a way to measure the effectiveness of challenges at scale when human labeling doesn't scale.
We created the post-authentication state model, which I'll refer to as the PASS model. It's a method for generating weak labels for accounts clearing fake account verification systems. PASS uses signals we can automate, for example, number of friends. This means it can be scaled, allowing both faster classification and far fewer human labels than a human labeling diagnostic approach would require. PASS has allowed Facebook teams to iterate faster with new features for verification challenges and scale experimentation launch and analysis, which in turn has allowed Facebook to maintain and improve its fake account defenses. PASS is a decision tree model which aims to emulate human labeling decisions, ultimately in assigning an account a proxy label. PASS is trained and validated against sets of human-labeled accounts using out-of-the-box classifiers based on the CART recursive partitioning algorithms such as scikit-learn decision tree classifier. The model assigns one of three possible states to the classified account: good post-authentication state, or GPAS, for likely real accounts with authentic signals; bad post-authentication state, or BPAS, for likely fake accounts with the intent to abuse the platform; empty post-authentication state, or EPAS, for accounts with too little signal post-clearing to yet make a determination. As mentioned in our introduction, online social networks enroll accounts suspected of being fake into a verification system in order to gain further information about their state. These verification systems, to evolve to match the adversarial response of attackers, they need to run A/B experiments. PASS classifies accounts clearing the verification system after a time delay so that we can understand how the A/B experiment affected the clearance rate of each population and decide whether to ship the new feature. An important note here is that the adversarial adaptation is not a direct concern for PASS itself, since this method is not used to take direct action on accounts clearing verification system flows. Rather, it's used to aid in experimentation and thus product evolution. Thus, that means there is no direct mechanism for adversaries to discover which signals to manipulate. We created multiple PASS models iteratively. We started with a simple proof of concept, which showed that we could create a classifier that was better than random assignment. The inputs to PASS models are attributes and behaviors that we can associate with the account. Account-level attributes include features such as the number of friends or email domain the account signed up with. Behaviors include post-clearance activities such as the number of friend requests sent or the number of times other users reported the account. The PASS models we developed were simple decision trees that remained static rather than being retrained. We wanted to understand how this tree performed initially and how it degraded over time. Behaviour signals such as time on newsfeed correlate to how engaged and how manual the account is, which in turn increases the likelihood that the account is a real user. We leave a specified time post-clearing to allow these behavioural signals to accrue. It aligns with the period we use to allow labelling signals to accrue before human labelling, so there is no decrease in the time to classification. The specific features in this construction can vary based on use case. For example, newsfeed could be swapped with another product users engage in other online social networks. Next, we tried creating a quick pass, a reduced classification time version of simple pass that provides signals more than 5 times faster than pass models and uses fewer signals than human labelling trees. The signals used are not contextual, unlike human labelling, so we hypothesise that the time to classification in pass is less significant. Quick pass has lower thresholds for behaviour signals, such as time on newsfeed, and omits some signals that take more time to collect, such as having subscriptions. To explore the stability of the system, we re-evaluated a simple decision tree in 3 months after it was first tested. In the table, we're comparing the top and bottom rows, Simple Pass v2.0 to Simple Pass v2.1. The main change was that the abusive precision dropped from 66% to 42%. The drop is caused by a mix shift in the underlying population. Our ground truth indicated that there were fewer abusive accounts and more empty accounts, potentially due to attackers choosing to let accounts sleep in response to concurrent independent work on improved detection. The reduction in abusive precision highlights the fact that it's necessary to monitor and retrain pass at regular intervals to mitigate the risks of changing behaviours. We evaluated quick pass in July 2018, comparing it with a simple decision tree that had no reduction in classification time over the same period. In the table, we're comparing the top 2 rows. Unsurprisingly, quick pass has lower F1 scores for abusive and benign accounts. However, as benign recall drops, we observe the empty recall increases. We believe this to be a result of the reduced time window limiting our ability to collect authentic engagement signals, which would ultimately disambiguate an empty account from benign for our expert human labellers. The simple pass decision tree model showed promise in terms of accuracy and latency. However, fake account detection and response is an adversarial space. Attackers adapt their approach over time to try and evade detection and deceive response verification systems. The consequence is that a simple decision tree model trained at a particular point in time will degrade in accuracy as fake accounts evolve. Moreover, training just once makes the model vulnerable to anomalies in the training data. The next iteration, pass production, was developed to address these limitations. Pass production uses an ensemble decision tree model to avoid overfitting. It is also retrained every day using a rolling window of training labels. This model uses scikit-learn bagging classifier combined with decision tree classifier. Like the earlier simple pass models, this model was trained with time to classification the same as human labelling. The goal of pass production was to make a more accurate and reliable model rather than a faster one. A quick pass could be developed in the same way as described before, by trimming the feature set and training the model with a shorter delay post-clearing. Since we take human labelling to be our ground truth, human labels provide the benchmark and optimal result for our models intending to classify users clearing our verification system. If we classified users with random assignment, then recall would be 33% for each class, and precision would be the prevalence of that class in the population of accounts. Random assignment provides a lower bound to compare models against. Any model with lower precision and/or recall than random assignment would provide no value and would even be detrimental in evaluating experiments. Our proof of concepts demonstrated that this approach could be valuable, each performing better than random assignment initially. Pass production strikes the best performance balance between classes and outperforms earlier versions. It is the only model to have F1 scores above 60% for every class. To verify our hypothesis that pass production is more robust than previous pass models that didn't retrain, we reran the evaluation of pass production 6 months later in May 2019. In the table, we're looking at the 2 blue rows at the bottom. The precision, recall, and F1 scores of all 3 classes remained above 60%, which no other model managed at any point in time. The largest drop was for the F1 score of the benign class, from 71% to 61%, changing equally between precision and recall. These drops might result from attackers increasing their efforts to appear real over those 6 months, as far as our automatable signals used in PASS can tell. Our human labeling process relies on more signals and it adapts over time, so we're still confident that our human labels represent ground truth. Retraining our models with new features could prevent these gradual performance declines. As the name suggests, we integrated PASS production into Facebook's environment to assess its usefulness in the experimentation process. When a change was introduced into Facebook's fake account verification system through an experiment, we used PASS to understand how the change impacted real and abusive accounts clearing the system. If the proxy labels assigned by PASS supported the experiment hypothesis, we would validate results with a small amount of human labels before launching the change. Without PASS, a significant amount of labels would be required to understand the effects of an experiment at different stages. Accounts have to be labeled early to catch failing experiments. In addition, accounts clearing in subsequent days have to be labeled to mitigate the effects of selection bias from the early stage labeling. Finally, labeling may be required to measure adversarial response several weeks after shipping a feature using a holdout. Pairing the PASS model-produced proxy labels with just one set of validation human labels per experiment for only those experiments we believe are successful reduces total human labeling volume. This method saves early-stage labels on all experiments, and it saves all labels required in clearly negative experiments, as PASS proxy labels give this information. We evaluated labeling volume over more than 120 experiments. PASS reduced the volume of human labeling required for experiment analysis by 70%. Additionally, as each of the launched experiments required substantially fewer labels, Facebook could run many more experiments in parallel. Quick PASS showed that we are able to get directional signal on experiments with significant reductions in the time to classification than human labeling requires. This early signal enables shutting down failing experiments earlier or requesting human labeling validation so that changes can be launched sooner. Quick PASS decreased classification time by 81% whilst keeping accuracy for each class well above random assignment. In addition to improving efficiency, the models were successfully used for automated monitoring in backtests of launch features. With this framework, Facebook discovered 3 cases in which adversaries eventually adapted to the new feature, which would manifest itself as a shift in prevalence in our model's proxy for abusive labels, BPASS, in the population exposed to that feature. This measurement allowed the team working on the verification system to quickly discover the underlying reasons for adaptation and mitigate the problem appropriately.
So fake account verification system challenges are an important part of improving OCN defenses. It is important to continuously iterate and measure effectiveness of the challenges. We need to measure the effectiveness of experiments at scale, even when human labeling doesn't scale. We have presented the post-authentication state, a method for evaluating changes to fake account verification systems. PASS uses a continuous retrained machine-learned decision tree model that proxies human labeling to classify accounts as abusive and benign faster and with less human labeling. PASS can be used to measure the effectiveness of changes in the verification system over time and to analyze A/B experiments which aim to prevent abusive accounts clearing or help benign accounts to clear the system. At Facebook, PASS reduces the volume of human labeling required for experiment analysis by 70% and decreased the classification time of accounts by 81%. PASS has allowed Facebook engineering and data scientist team to integrate faster residual features for verification challenges, scale experimentation launch and analysis, and improve the effectiveness of verification systems at remediating fake accounts. We mentioned that fake accounts is a generic term that can cover several types of abusive accounts. A high level of taxonomy would be bots and manually driven fake accounts. Being able to further divide our abusive labels and further divide BPASS, our proxy label, into abusive bots and abusive manually driven fake accounts would greatly help to optimize challenge selection in the verification system. For example, there could be challenges that are trivial for humans and difficult for bots. For example, well-designed captchas. And there could be challenges that may be solved by bots, but that are humans. For example, a time-consuming verification. If we were able to measure whether a fake account was a bot or a manually driven fake account, then we could assign challenges properly. Thank you.